All right, so what you'll need out here is that periodic table as well as the your notes. So we're just going to talk about a couple things here related to compounds. What? Yeah, it's a page that looks just like this, has radicals at the top. So we talked yesterday about metals and non-metals forming pretty simple compounds. Just you have two elements combining with each other, a metal and a non-metal. Those are called binary compounds. But compounds can be much more complex than that with other multiple atoms of various elements. But we're not going to get into too many details. But we will talk briefly about something called radicals. They're also called polyatomic ions. And radicals are a group of atoms that sort of acts together as if it were one single atom of a single element. And so sometimes these can form compounds with other elements. And what you're going to do is look them up on your list. So on the back of your periodic table, you'll be given this on your quiz. What you have is a list of common radicals. It tells you the name of them. It gives you their formula. And it tells you their oxidation number. You just have to look it up. And then these act as any other element would act. Usually when we're putting them in a compound with another element, we keep them in parentheses to symbolize that they sort of act as one unit. So as an example, let's look at this first one here. We have nickel. And what is PO4?
Phosphate.
Phosphate. It's on the radical chart. Okay? And so you could find it there. So nickel, what is nickel? You'll have to turn over your periodic table. What is nickel's oxidation number? Raise your hand if you can tell me the oxidation number for nickel. Derek? +2. Raise your hand if you could tell me what's the oxidation number for phosphate. Bella? -3. It's on your chart. It's on the back. Not phosphorus, phosphate. So it's on the back of your periodic table. It's on the radical chart. It's -3. And then we do the same steps. We do that crisscross. The 3 comes down to go with the nickel. The 2 comes down after the phosphate. We keep the phosphate in its parentheses, and that's our compound, nickel phosphate. Okay. This 2 goes with everything that's in the parentheses. So it goes with all of that. There?
So you're doing the same thing, just you're keeping the number in
Yep.
parentheses.
You're doing the same thing. You just keep this in parentheses and look up the oxidation number rather than figure it out from the periodic table. Colin?
Would phosphate be capital P and O, or is that supposed to be lowercase?
No, because this is 2 separate elements. This is phosphorus and 4 oxygens all together. If it was P lowercase o, that would be polonium. That's an element. Okay, so that's why capital lowercase is important when you're writing the symbols for these elements. Jaden?
So why are phosphate and phosphite both PO?
Because there's different amounts of oxygen. And we'll talk about that in a second. All right, here's another one. NH4. Raise your hand if you could tell me. What is its oxidation number? Campbell?
+1.
Yep. It's on the radical chart. It's +1.
Ammonium.
Yep. And how about CO3? Arpon?
-2.
-2. Do a crisscross.
Wait, you say
And we get an H42, CO3. Ammonium carbonate. So when we see those radicals in parentheses, we just look them up on the radical chart and use them the same way we would use another element when forming a compound. Now, we are not going to get into a lot of detail. I just want to give you some simple rules when we're naming these metal, non-metal compounds. Okay? You know, someday, maybe in college, you may take a class called organic chemistry, in which you spend a lot of time memorizing structural formulas and the names of lots of different types of compounds. Lots of times it's people's hardest class if they're in like a science majors or organic chemistry. But anyway, we're just going to talk about some very simple rules. So when we're naming these binary compounds, these metal, non-metal compounds, which we've been talking about, to give them their name, you start by just giving them the first name of the metal. For the second non-metal, usually we change the ending from what it is in the periodic table to "ide," and that gives us the name of our compound. For example, if we take sodium and chlorine, we would say take the first element, sodium. We take chlorine, change it to chloride, and we have sodium chloride. That's the name of this compound. Sodium is a metal, a soft metal. It is extremely dangerous. It is explosive. If you have pure sodium metal and you were to get it wet, it would burn and explode. It has to be, if you have pure sodium metal, you have to keep it in a container covered in oil so that no water can get to it. Like this is sodium metal. Chlorine is a deadly gas in its pure gaseous form. Chlorine is toxic. It was used during World War I as a weapon, okay, to poison troops. So it's dangerous. When you combine those two, a explosive metal and a toxic gas, doesn't sound like something fun, does it?
Don't forget.
But what is it, Bella?
What?
What were we going to say? You have a question?
Yeah, isn't the thing that you put in your pool chlorine?
Yeah, it's a different form of chlorine, but chlorine, the element is toxic to living things, and that's why you put it in your pool, but at concentrations that are strong enough to kill bacteria and algae and things, but not strong enough
So
to
if
hurt a
you drink
person.
the water,
There.
is there between sodium, like that sodium and sodium?
Yeah, the sodium you put in your food is combined with other elements. What about sodium chloride, this compound itself, Danielle? It's just salt.
Oh, wow.
We're eating dangerous stuff every time we eat
So, the reason I bring this up is to drive home the point that, yes, sodium is an explosive metal. Chlorine is a deadly gas. But when two elements form a compound, their properties can completely change. That obviously salt is not dangerous. It's something we use all the time, used as a preservative. So the properties of a compound aren't the properties of the two elements sort of mixed together. Can have completely different properties. Okay, so that's why I bring up that example. Arpa?
So is like, that the reason why people tell you to shovel it immediately after you go to the pool?
Yeah, because like if you had too much chlorine in a pool, it can irritate your skin and so forth. Again, the chlorine you put in your pool is not just pure chlorine. We just call it chlorine, but it's a compound containing chlorine.
Wait, why does it turn your hair green?
I don't know, there's some reaction that happens sometimes with
My
certain
hair turned green
people's hair.
last summer.
Jaded?
So like, is there anything like where you can take two super safe, like elements and then turn them into like something
Yeah.
dangerous?
Yeah, if you take carbon, which something we eat all the time is in almost everything around us, and oxygen, obviously we need to breathe, combine carbon and oxygen to carbon monoxide, and you have a deadly gas. You have a carbon monoxide detector probably in your house that will, because it's odorless gas, but it can kill you. And so, yes, that's sort of an example of that. Joe?
Where would you find like pure sodium?
I mean, you can get it through like a science catalog. If you go on YouTube, maybe at the end of class when we get our work done, I'll show you a video of people, they threw pure sodium in a pool. See their reaction.
Why does sodium want every?
All right, we need to move on now. We'll watch that video later. Sometimes we also will use the certain prefixes, not only to tell us which elements there are, but to tell us how much of each element there is. So, for example, carbon, CO2. We start, that's a metal, non-metal compound. We give it first the name of the metal, carbon. what do we change oxygen into?
Carbon.
Oxide, but we also give it a prefix to tell that there's two of them.
Dioxide.
Di is a prefix for two, carbon dioxide. So,
Wait, what's that carbon?
Fiber does form.
Is that one that's carbon
No.
that has a dye in it?
nope, di just means two. Polyatomic ions, so those radicals that we just talked about. If you look at their names, you'll notice there are some common endings, like carbonate, or sulfate, sulfite, phosphate, phosphite. So those endings also indicate the 8 version, phosphate, has one extra oxygen atom in it than the 8. So if you look at phosphite, what's the formula?
PO3.
PO3, phosphate is PO4. Okay? Chlorite and chlorate, same thing. So let's, Jaden,
Do you use carbon to make like carbon fiber?
yeah.
That's so pretty.
All right, so let's get some practice here, naming some of these compounds. So we already did this. NaCl, sodium chloride. What would we name MgO, Derek?
Magnesium.
Oxide. How about magnesium and bromine? Griffin?
Magnesium and bromide?
No?
It's not. It's like, yeah,
There's 2 of them also.
I can't pronounce it.
Joe?
Magnesium bromide.
No?
It's like
Not bromide.
Yes. Magnesium dibromide, 2 bromides. Lithium and sulfur.
Sulfate.
Jan?
Lithium sulfuride.
Close, but there's 2 lithium.
Oh.
So
Lithium with.
Dilithium sulfide. Any Star Trek fans in here? The warp drives run using dilithium crystals.
Oh,
yeah.
Where'd you get those?
I don't watch it.
All right,
Show me
beryllium. What about this one? Now this one's a little more complex.
So.
It's beryllium, sulfur, oxygen, 3. it's
So,
beryllium
too many
sulfide.
words in there.
Beryllium
What is SO3?
Oh, it's
Yeah, it's beryllium sulfite. Where do you find the name of SO3?
sulfide.
It's on your radical chart. So when you see these with multiple elements, it's probably a radical from your chart. You just have to look it up.
So what's it called?
Beryllium sulfite.
Wait, sulfite?
Yes.
Have you seen the orbital?
That's hilarious.
All right. How about this one? Elbow 3.
Elbow.
What would we call that? Raise your hand if you can tell me the name of it.
Oh. You call me first?
Camel?
Aluminium. Is it boron, oxygen?
Nope. Arpon?
Aluminum, boron.
It's aluminum.
Nope. Too many words in here. Kara?
Aluminum borate?
Yes. Aluminum borate. BO3 is one of those radicals. It's on the back of your chart. Echo 3.
Borate?
Borate. How about this last one?
Calcium?
Wait, calcium.
Calcium carbonate?
What's that?
Calcium carbonate?
Calcium carbonate.
Calcium carbonate.
Right.
All right. We'll get a little practice here in a minute. First, bonus question.
There's 3 of them.
There is a special prize for this, answering this question.
Is it, I think it's
You must raise your hand.
Man,
Tell me the occupation of a fictional character who was once frozen in carbonite. the occupation.
Wait, it's a job.
I know. Pick him. I know exactly.
Bowman.
Period.
Dead.
What?
Dead.
Dead?
Wait.
No. Griffin.
He was a news reporter. He worked in like a magazine.
No.
That was after.
No. No.
Is it?
Joe?
I'm sold.
That's not an occupation. Campbell?
Deceased. He saved lives and he had a.
No. No. Jaden.
Wait, what was the question?
The occupation of a person that was once frozen in carbonite.
I said kryptonite.
Oh.
Not kryptonite.
Oh my God.
Griffin.
He's a smuggler.
Yes.
Dang it,
I don't get it.
He's dead now. He's dead now.
Yeah, that's not an occupation. Deadness.
Good.
All right. Griffin, your prize is a sticker of his son.
Oh,
Who is his son? Oh, sorry. Spoiler alert.
It's Ben something.
In case you didn't
It's
see.
Ben Solo. It's Ben Solo.
I thought you were talking about Captain America.
Carbonite. Han Solo's frozen in carbonite, right? By
I thought you said like underwater.
Darth Vader.
Like,
What?